Welcome to week 7. This week we're going to mostly talk about different types of modeling techniques for prediction of 3D structures of proteins, primarily homology modeling. Uh, we are going to look at the different parameters that we look at while doing different types of modeling. So, for example, in homology modeling, we look for sequence identity and so on. So how do those parameters actually predict the structure compared to randomly predicting the structures? And yeah, one thing to note is that basically all the tools that we are going to talk about uh, are basically some are legacy tools, some are quite recent, but I think none of them performs as well as AlphaFold or the very new deep learning methods that is there out there predicting protein structures. But again, so in deep learning, it's mostly how people use it as it is very hard to understand what the model is actually doing inside the whole procedure. So it becomes some sort of a black box in terms of you don't know what is happening, but you know what is happening is correct because you have accuracy results. And ultimately, yeah, you can use it to predict anything. But the idea is that you do not completely know what the model is actually doing, what are the patterns it is picking up to predict a particular structure. Uh, for our cases, we're going to learn the basics of that. We're going to learn what parameters or what features of a particular protein or an amino acids are important to predict the structure and how the properties of those amino acids actually confer the structure to the protein itself. So let's get started. Again, I'll start with the very old saying of the protein folding problem. So this has been there for like I think since the 1960s or 70s, after which could uh, we could use X-ray crystallography to see structures of proteins and so on and so forth. So, roughly around the time DNA structure was discovered. So, this problem has been there for a very long time. So, the experimental procedure to find the structure of a protein or how a sequence of amino acid fold upon one another, um, it it is the problem is known as the protein folding problem, and the main the experimental techniques used for it are mostly X-ray crystallography and NMR spectroscopy and all those other methods that we talked about in last classes. But uh, the thing is, those techniques, if you want to go for experimental techniques, most of them are very expensive, and you have these hundreds of different proteins, right? Hundreds and thousands of different proteins, and if you want to do crystallography for each of them, it becomes more like it very extensive in terms of both financial, and it becomes very difficult to it will be very time consuming to predict everything. And the second use case comes is basically what happens if there is a mutation in the protein? What happens if in a particular long residue of hydrophobic amino acids, the mutation causes a few amino acids to change and become some polar amino acid or some hydrophilic amino acid? How does the protein folding change? Now, specific if you want to study specific mutations, how specific mutation can change the folding of a protein. Ideally, experimentally, what you should do is basically take the crystal of a protein that has been mutated in this exact same position and try to see uh, the, uh, the the structure of the protein in crystallographic technique. But what can happen is, in some cases, if the mutation is dangerous enough or if the mutation is deleterious enough, what it will do is basically it will misfold the protein, and the cell inside the cell won't tolerate misfolded proteins, right? So what it'll do, it'll tag a ubiquitin on that protein or something else, and it'll basically destroy the protein. So it is very hard to get. It is going to be very hard to get a protein with a mutation which does not actually is not sustainable, right? So all of these different scenarios, the ideal way would be to see if you can predict the structure of a protein from the sequence itself. So if you know the sequence, can you predict the structure of the protein? And if you can change certain amino acids in that sequence, how does the protein folding change, right? So technically, it is theoretically possible, right, to predict that. So that is what the protein folding problem is. So it is theoretically possible to predict 3D structures of a protein just from its amino acid sequence. However, it is extremely challenging because of the sheer number of possible conformations. And AI is basically artificial intelligence is basically best suited for this, as are the softwares like AlphaFold and all of those. So it because you have to consider all the different possible conformations a particular protein can have and be stable in those conformations, it is often quite hard to predict the structure of the protein. So that is the reason why till like 50, 60 years after getting crystallographic and predicting structures of protein, we without using AI, it is still very difficult to predict a structure of a protein just by the sequence itself. Now, if that sequence is similar to another protein and you can do some homology modeling, we'll discuss about that. That becomes a little bit easier. But if your sequence is novel, completely novel, and you have very less sequence similarity with other proteins, it is almost an impossible task to predict the structure, right? Just give me a moment. I'm getting an important call. Just 2 minutes.
Sir, sir, excuse me, sir. Are you able to hear me? Sir, are you able to hear me? Hello, sir? Sir, can you hear me? Hello, sir.
Can you hear me now?
Sir, we were able to hear you, but I don't think that we were audible to you.
Yeah, I did not hear anything.
Yeah,
Were you
because
able to
I
see my
was
screen?
trying to tell you that about 20 to 25 minutes we were not able to see the presentation, and we didn't see the all the interactions like Gibbs free energy and all of that. Also, but we were able to hear you.
Okay,
We
okay.
got the.
I'll quickly go over the topics that you
You
raised.
can
So
just show the slides because we get the gist of it. That you were trying to explain the interactions and whatever, like energy, enthalpy, and all.
okay,
But we were not able to see the presentation.
okay. I was also not able to hear. I think there was some issue with
Yeah,
my
it's all
phone.
right, sir.
Yeah, I think the screen was not also properly shared. Now can you see the screen?
Uh, yes, sir.
Yeah, I'll just quickly in 5 minutes I'll go through it. So where is the last what is the last slide that you guys had seen?
Sir, I guess Dali method after that 1 to 2 slides.
Okay,
I
okay,
guess.
okay.
Yeah,
I'll
this one was the
okay,
last.
okay, okay, okay. I'll quickly go through those, but before that, I think there's a lot of questions here. Is there any uh, particular question? Uh, yeah, DALI method is still used, but again, as I was saying, it is not very like it does not hold up to the deep learning methods, right? So, but yeah, it
Sir,
is
today nowadays for prediction we give the sequence to AlphaFold and
mostly yeah.
it
After
just goes
AlphaFold,
for
it
you.
is the benchmark, right? So, whatever we
Because
are doing
AI
this,
after 2024, AI is
yeah,
being introduced in
yeah.
AlphaFold.
Yeah. So
Yeah.
there is AlphaFold and there are different models of AlphaFold as well. So one of them is basically alpha genome, which can predict in terms of if you give a particular variant, it can predict the change in the change in the structure of the protein as well. So they have come a long way in terms of predicting the structures. Firstly, they have predicted all the known sequences uh, uh, of in PDP, and also they are now going for like mutated sequences. Uh, uh, all the possible mutated sequences that are possible in terms of different variants, and they're efficiently able to predict structures which would we would have not been able to do in most cases, because in these cases we need homology modeling or other kinds of similarity metrics to say that this particular protein is going to fold like that or not. But in case of deep learning methods, it is not required. It just does it all by itself. Okay. Uh, okay. Okay, I think there's this question, right? Okay, GPGP and KK are basically these are what you are asking are basically peptide linkers, right? So uh, these actually affect. So we have not discussed these set of things in great detail, but uh, KK linkers or GPGP linkers, they are actually used when you're doing these predictions on say for example in homology modeling and those kind of things. These things are considered. They they are considered in terms of how they can affect the sidechain looping, or how they can affect long range and short range contacts as well. So because you have these linker peptide sequences between two set of amino acids or other very far away located amino acids in the sequence, this can definitely change the conformation of the protein. But these are at a level, you can introduce these things once you know the basic structure of the protein. Once you can actually accurately predict at least what the basic structure will look like, then on top of that, you can add this set of complexities. There can be thousands other complexities uh, that are present. So definitely they contribute to the structure prediction, but not at the very basic level. So at the very basic level, you make a structure, say that this is quite accurate. On top of that, now you add all the possible uh, modifications. In some cases a lot of amino acids are modified, right? In some cases some peptides will have multimeric structures. It will have, so for example, histone is an octameric protein, right? It has 8 subunits, and so those are all levels of complexity that come after the basic modeling procedure, where you can get the basic structure of the so basic structure of the protein, and then on top of that you can add the complexities. Yeah, but yeah, definitely they not change, but they obviously play a part of the for prediction. Okay, sorry for these things, but yeah, I'll quickly show what is there. So yeah, basically I was discussing uh, the different parameters in terms of the, the parameters that we use to say a particular structure, how good it is, how bad it is, and how we quantify it in terms of its steric uh, locations, and also in terms of its energy states. So in terms of steric locations, you can use center of mass, which is basically uh, mass times the location divided by the total mass. So it will give you where around the whole protein is based on. You have radius of gyration. Radius of gyration tells you the farthest point away from the center of mass. So if the radius of gyration is more, it is more spread out. If the radius of gyration is less, it is more compact and more uh, more compact and more close together. And yeah, we have different contact ranges, so those also come into account, because a particular amino acid from, say, the fifth position might be in contact with a particular amino acid in 200th position, and so on. So there can be these long range and short range contacts, which are very important for stabilizing the structure. So we need to take those into account as well. So here I was discussing this PDB param paper. I don't think you could have seen my screen, but yeah, these are all the parameters that has been described there, and I think this is the paper from Sir. And if you go to the methods, they tell you what are the parameters that they have considered. So interresidual interactions, short, medium, long range contacts, number of contacts, uh, propensities in terms of percentage of alpha helices, amino acid compositions in different turns, physiochemical properties including center of mass, radius of gyration, hydrophobicity, which is very important, surface hydrophobicity, and accessible area, SA that we discussed last time, uh, buriedness of the motifs of the amino acids, also we have discussed earlier, and so on and so forth. So there are a host of parameters that they use to quantify how good or how bad the protein has been folded or not. And then you have this hydrophobicity indices, hydrogen bonding parameters, and so on. So a huge chunk of these parameters are involved in predicting how good a particular protein structure is. Okay. Yeah. After that, yeah, we talked about this in terms of the energy, in what different types of energy we are looking at. We have electrostatic, van der Waals, hydrogen bonding, hydrophobic interactions, so on and so forth. So these are your uh, enthalpy and entropy measures. Then you have your uh, uh, different types of delta G plots. So if you go from denatured to folded state, the delta G is going to be negative, and if you move the other way around, it is positive. So yeah, so the protein is more stable in a more folded. state, right? And then you can have a protein is can only be present in a folded or an unfolded state, and if you add the fractions up, it is always going to be one. And then you can have a weighted you can put weights on these fractions in terms of uh, yeah, across different concentrations of a particular, if you're doing denaturation across different concentration of the denaturant, the observed value at any point is weighted average of the two states, right? So depending on the type of protein and the type of denaturation that is happening, the weights will be decided by that. So this is what is known as fluorescence intensity. Then you can look for thermodynamic stability, which is the delta G equation, negative RTL and K. Then we look for electrostatic interactions, which is Coulomb's law, Q1, Q2 by R squared. You can have these ion pair bridges where you have bridges between your positive and the negatively charged residues. You need to consider those as well. Hydrogen bonds and van der Waals radius. The van der Waals forces are very weak in nature, and it scales away if slight increase in distance is present. And again, hydrogen bonds, as we all know, it's a covalent bond between uh, the negatively charged oxygen and the positively charged hydrogen involved in covalent bonds inside their own molecules. And then we have the hydrophobic free energy. This is very important in terms of like how much of energy difference in terms of hydrophobicity we have compared to folded versus unfolded. And the in the individual atoms will have also some solvation parameters that need to be considered. And after that, basically, the disulfide bonds of methionine and cysteine, which bring stability. This also falls in that. Someone asked about the GPGP and KK linkers. Disulfide bonds are kind of similar to that, but disulfide bonds are short range, and the linkers that you are talking about are mostly long range. So yeah, but all of them actually play a part in modeling the structure. And yeah, so again, the important thing that I left with is basically the unfolded state of the protein has higher entropy, but we are moving from unfolded to a folded state where we are reducing the amount of entropy required. So yeah, that is something to be mindful of. And if you do a regression of the delta G across the different delta Gs that we discussed in terms of hydrophobicity, in terms of electrostatic interactions, in terms of van der Waals radius, sulfide bonds, and so on and so forth. If you do a multiple regression like that, it comes out that the hydrophobic interactions are actually the primary drivers of this energy change, which is the delta G. So the whole delta G is more affected by the hydrophobic interactions than the other interactions, at least in a statistical manner. But this does not reflect causality, or this does not say that hydrophobicity is more important than electrostatic interaction in terms of protein folding. It's just that from the statistical point of view, the contribution of hydrophobic interactions is more compared to much more compared to the other interactions that we look at. So yeah, I think that was
So
all.
this
Yeah.
also doesn't account for salt bridge formation also, right?
Now, so this does not account for a lot of things. It's just a simple state equation that has been given by sir. But you can keep on adding delta G's in this equation. You can add more or less like 50 more different factors to this and then do the calculation. But if you're so the idea is that we are going till 1%, 1.5%. I think, yeah, the disulfide interaction is given here. But if you move beyond that, if you are looking for something like, say, for example, salt bridges or something like that, or if you do mm, something else,
For
mm,
example, porphyrin rings such as ligands, we have
sorry.
different types of we have ligands like porphyrin rings
Yes, yes,
in
yes. So
hemoglobin and
usually you
different
can
kind of
you can take into account hundreds of interactions and then try to find what is the most important causal interaction. But again, it won't go beyond the hydrophobic interactions, which is basically the primary driver for the protein folding thing. There are mechanistic insights about why hydrophobicity is the most important, because if you think about it intuitively, the hydrophobicity of the residues will determine which side the sequence folds, right? So it is true for protein folding, it is true for membrane dynamics in the cell membrane. It is true for any kind of interactions inside the cell. Hydrophobicity most of the time is the primary driver behind certain folding or certain conformations of the molecule. So even if you keep on adding stuff to that equation, I doubt it will change much of the contributions from the rest of them. Maybe slight changes, and they'll be uh, the betas of those interactions would be in like less than 1% range. So probably lower than this. But yeah, we need to account for those. At that level, less than 1% is also an important driver, right? So we need to account for as much as possible. This is just to show in terms of uh, the statistical technique that the most important driver is probably hydrophobicity. So yeah, it's just to show that it is not a very well established equation. You can put in a lot of variables. You can make this equation much more robust. So this is just for an example. And yeah, so uh, it is again, so it is again 0.28 kilocalorie per mole when compared to the experimental delta G data. So this is quite close, but you can be much more precise in terms of the interactions that you uh, consider for the protein folding. Okay. So any more questions? Okay, then we'll move on to the question. Move on to the. By the way, where was the previous week's question? Previous week's only, I think. Question, was it resolved by the other uh, in the other live session, or
Sir, due to some reasons, he was not able to take class yesterday, so the class is postponed for tomorrow.
oh, okay. You can ask him then probably. Okay, I'll just be back in a minute. Okay. I'm audible, right? Am I audible?
Yes, sir.
Yeah, okay.
Yes, sir.
Okay. Yeah, I think Cat was from the last session's last week's part. I'm not sure if that's been covered in this week. But anyway, so it stands for class architecture, topology, and homologous superfamily. And so, yeah, it's the correct answer. Sequential connectivity of secondary structures. Okay. Yeah, this we just discussed a few minutes back. correct. Yeah, 5 to 25 is the correct answer. Delta G is between 5 to 25. These are the things probably you need to remember for answering this set of questions. So, yeah. So, one thing to keep in mind is the number is not very high. The reason behind that is because of the entropy. Because you are moving from a high entropy state to a low entropy state. Although your delta G is negative, you're moving to a lower entropy state. So there is some contradiction to that. So that's why that number is not very high. Ideally, that number should have been very high. But since the entropy is going in the opposite direction, so it is not very high. Okay. Sorry. You guys said B or A? Ah, okay, a lot of B. I'm not sure why it's B, but circular dichroism is definitely used because it changed. It is basically uh, checks the difference between absorption of right and left-handed circular polarized light by the chiral molecule. So that is definitely used for folding, measuring the folding free energy. I'm not sure about isothermal calorimetry. All of you are answering that. So is this been discussed or anything?
No, sir, but I thought that it was isothermal.
Okay, I'm not sure. Um,
So maybe I got confused with free energy or temperature, I guess.
I
That's why
think
I'm
binding constant, enthalpy, entropy of ligand protein interactions. I think, yeah, this is used. It seems like it is used to check for delta H for enthalpy, but I don't think it is used for checking directly energy. Free energy is, I don't think it checks because it checks the enthalpy is from what I can see. Enthalpy change, delta H. So here we discuss those things, right? So uh, where did it go? Yeah. So what it is measuring is delta H. What we need is delta G. And I don't think it measures delta G. I'll take a look at this. I'm not aware of this procedure. Mm, But
so
circular
maybe we just
dichroism
got
is
confused.
circular
It's just that
dichroism is
you might be right because
straightforward
we
thing.
maybe got confused with thermal folding
Uh,
and free energy, right?
and I think circular dichroism has also been mentioned a few times in the lectures as well. I think, right? If I'm not wrong, I think I heard them in the lectures as well. Okay, but the answer given is circular dichroism, and circular dichroism is definitely used for measuring folding free energy. Isothermal calorimetry looks like is measuring delta H, not delta G. So yeah, but both are measuring some sort of energy change. So yeah, be careful with these type of questions. Okay, I'll check this what this is. I'm not very sure about that. Okay, yeah, this should be easy. Okay, yeah. So those rotamers are the ones that we are looking for. So there's a library of rotamers that they look for in terms of when they want to get a site model. And these rotamers are basically conformational isomers. So it makes life a little bit easier for them. So yeah, aromatic is the pi interactions, right? So mm, okay, somebody answers. See, electrostatic, it gives hydrogen bonds, it gives aromatic pi also it gives. So if anybody of you are confused, I have given the link to the paper. Please take a look. It has all the, you look at this materials and methods section. It has all the parameters given in that, whatever everything they are considering. And I think they're considering all. So yeah, the answer is all of the above. The pi is also there. This again, Hmm, I think, yeah, it was there. Yeah, I get confused by this particular symbol, particular sign. Is it positive or negative? It is negative. You're correct. It is the first option. Remember the 12 and the 6, that is important because some question might come like in terms of how is it proportional? Like not giving you the exact equation, but it'll ask you how it is proportional to the power of what. So negative 6 and negative 12, please remember that. But yeah, option A is the first option is the correct answer. Yeah.
Sir, we have is numericals based on these formula is expected.
See, there is whatever. So these set of questions are basically previous year's assignment question, right? So that nothing is here as per se in terms of numerical based questions, but some questions might come. So delta G questions definitely can come, right? So delta G questions are given the parameters. You're just asked to find delta G negative RTL and Q or whatever um, uh, thing that you're using. Delta G questions can definitely come. I think there is one question here as well. Other than that, numericals I have not seen much, but I would not say that it won't come. At least you might not have to those might not be very difficult numericals. You might just need to plug in the values in a formula and find the answer. In most cases, it will be like that. So the idea is that you remember the expressions, the equations mostly. If you remember those, I think it is good enough because even if numericals come, it will just be a plug in the value and find the answer. And it like not very difficult computation will be required. So like as I was saying, some you probably won't need calculators and those kind of things, but the equations you should remember. Here, for example, a question might come like uh, you're given a proportional value and asked like you're given a value and you're going to be asked what will be the van der Waals radius proportional to, like that. So the r to the power 6 and r to the power 12, negative r to the power 6 and negative r to the power 12 are important to remember. So those kind of questions might come. But I have not seen very difficult numerical questions in and around these things because these are the old assignment questions and like I could not see any very difficult questions like those. So I don't think you need to worry about that much. Okay, moving on. Yeah, so for example, this type of questions might come. Say a couple of A's, okay. Wait another minute. I think you need to be careful about the signs, positive and negative. What does release to 50 kilojoule? mean in terms of the sign? Do we have any other answers? We have a B and a D. Okay. I think D is the correct answer, if I'm not wrong. Yeah. So releases 250 kilojoule is negative. Delta U is negative for that. And you have a positive work. So you're finding delta H, which is negative 250 plus 50. So that is negative 200. So when you're saying it is releasing energy, delta G or delta U or whatever uh, energy difference that you're saying, it is going to be negative. The release of energy is always negative, right? So keep in mind the symbols of like positive or negative. Okay. Answer is project. I think somebody answered Swiss model, if I'm not wrong. Yeah, somebody answered Swiss model. Swiss model will only give you the template. Swiss model uh, does not give you the validation. ProCheck will give you the validation. Swiss model will give you the template, which you can use. Your basically your homology modeling template, which you can use to model your protein, but it won't. It does not validate anything. ProCheck is the software for validating. So yeah. Okay, see, wait another minute. Sorry. Yeah, both are negative. So the idea is that you have it easily mixes with water. So the mixing with water, the solvability in water is favorable. So you have negative energies for both nitrogen and oxygen. Uh, yeah, it is favorable. This is a simple numerical, I think, uh, can attempt. Okay, let's see E, C. Okay, yeah, here you just have to. So nitrogen, uh, yeah, for nitrogen it would be what is that? 12 times this plus this divided by, yeah. Okay, yeah, you just plug in the uh, 6.3, 6.4.5, and 9.5. I think uh, A is the answer, if I am not wrong. Just a second, what answers did you guys give? Okay, there's a A and there's a C. I think, yeah, A is the answer. Yeah, so this is a weighted average, as you saw. So 14 is basically 14 is for nitrogen. So 14 times 5.3, x coordinate, y coordinate, and z coordinate. Uh, mm, this is 54, okay. 10 times 5.3. Yeah. So 14 times 5.3, 12 times 6.1 is the alpha carbon, C alpha. It's okay. 12 times 6.1, 12 times 7.4, it's fine. And 16 times 16 times 6.4, yeah. So you add this up and the total molecular weight of everything together. So there are two carbons, one nitrogen, one oxygen. So 54, you divide it by 54. Yeah, I think this is the level of answers that you're going to get. 6.3 around, 4.5 and 9.5. So basically you're multiplying, it's a weighted average, right? So for nitrogen, the first coordinate would be 5.3 times 14. This is actually carbon only. Ca is the alpha carbon. So 6.1 times 12 and 7.4 times 12 again, 6.4 times 16. And similarly for y coordinate, similarly for z coordinate, and you divide by 54, which is the total molecular mass of the compound. And yeah, we're going to get these coordinates. Okay, everyone got it? I hope everyone got it. Okay then, I think, yeah, that is all from my side for today. If you have any questions, please ask, or else we'll close the session. Okay then, thank you for joining. See you next Tuesday, same time. Thank you guys. Have a good week. Bye.
Thank you, sir. Bye.